So my name is Tony Chen. I'm a solution engineer from Keyfactor. So last year I was here in the OpenSSF Community Day. I covered post-quantum, quantum-safe algorithms and its readiness. Today I will just do a little bit recap, and then we will dive into our main topic today, which is interoperability for PQC. So here's a quote that I took from NIST publication. It says, the security of cryptographic algorithms is constantly challenged by the increase in computing power and the sophistications of quantum analytic, cryptoanalytic techniques. So we've seen this many times historically, right? So from triple dash to AES migration, SHA-1 to SHA-2, multiple times upgrading for RSA keys from 1,000, 2,000, and now it's recommended 3,000 keys, right? So the constant cryptographic upgrades and migration has been always been a part of the cybersecurity landscape. So as many of you already know this, quantum computers, because when quantum computers are capable enough, it breaks the cryptographic that we use today, for example, RSA and ECC, right? So NIST from US has released the standardized post-quantum algorithms last year. So we have MLDSA for digital signing, for MLChem for key encapsulation, and key agreement, and SRH-DSA, which is stateless hash-based digital signature algorithms. And also this March, NIST also announced HQC as the fifth standardized post-quantum algorithm as the backup for MLChem, which is in the case where MLChem found vulnerable in the future, at least we have a backup algorithms available. NIST has been working on more quantum-safe algorithms to be standardized in the coming months or years at the moment. So migration to quantum-safe algorithm and cryptographic is inevitable. So what timeline we're looking at and what other countries and leading institutes are doing. So we can see USA, NIST is leading that discussion, right? So they have indicated the timeline to deprecate RSA and ECC by 2030, right? And by 2035, RSA and ECC will completely disallowed. I put the link there, or the name of the publication there, so you can do a reference check. In UK, leading by NCSC, they have a timeline by 2028 to complete, for organizations to do complete inventories and at least some plannings for PQC migration. By 2031, there will be a early migration for critical infrastructures and for PQC migration. And similarly, by 2035, there will be full migration for a lot of infrastructures. Australia, leading by ASD, SCSC, they have similarly 2030 timeline to deprecate RSA and ECC, as well as SHA-2. So you have to upgrade the key size, so that's the SHA size for security. Japan, I did my research. Unfortunately, I couldn't find any timelines indicator, but if any of you have any ideas around the timeline, let me know. We can discuss about in details. But in general, government agencies are urging organizations to shift to PQC. So we're talking about massive migration for cryptographic to classic PQC algorithms like RSA and ECC to post-quantum quantum-safe algorithms. And that's the concept of crypto agility comes in, right? So what is that, and why do we need crypto agility? Is that only for cryptographic migration for PQC? The answer is no, right? Because it's all about being able to adapt your cryptographic system quickly and effectively. And we have seen cases where last year, one of the biggest public CA entrust was distrust by major browsers. So organizations have to shift from one vendor to another, and that's involved a lot of cryptographic change and certificate renewal and re-enrollment from different CAs, for example. And it is also about to minimize the risks and disruptions. So if there's a vulnerability in terms of cryptographic and any certificates are expired, so we organization need to replace those certificates and cryptographic quickly to mitigate the risk. And in the industry, we also seeing this certificate lifespan has been shortened over the years, and there will be 47 days by 2029 for public certificates. So it's impossible for a human being to renew those certificates manually anymore. And of course, the massive migration from classic algorithms to PQC is definitely required crypto agility. Right, and of course, PKI is definitely vulnerable to quantum computers. And PKI migration is, in general, very challenging because there are certificates and keys living in the devices, and the root of trust and be embedded in the organizations, or it can be, in the IoT devices. So we're talking about that level of migration. So we need to consider different strategies and approach in terms of PKI. I have listed out 4 different approaches. So the first one is to completely migrate from the classic algorithms today to quantum safe PKI. It doesn't make sense at the first, but this for is very it make much more sense for some of the industries, especially for manufacturing industries. Transitional, we are talking about running the legacy algorithms and PKI at the same times with quantum safe PKI. So that's where when you control the ecosystem that you can do that. But if you're an organization that you have clients connect to your services, you don't have the control of your ecosystem. You need to make sure the compatibility of the TLS connections and all this, and that's where you have to consider a hybrid approach where we can use hybrid PKI, hybrid CA to issue hybrid certificates to ensure that any connections that is able to connect to the system using the legacy algorithms like RSA, but if some of the clients using more advanced quantum safe algorithms, they can still connect to the system. And compensate is a complete switching from classic PKI to a non-backward compatible PKI, which is more technical in that sense. I'll try to skip that details. So within Key Factor, we have been developing our solutions, and we have the full suite of quantum-ready solutions. It is also available open source. So Bouncy Castle, so the solutions in the middle box, Bouncy Castle, EJBCA, and Science Server, they are available as open source. Just a quick check, anyone heard about Bouncy Castle, EJBCA? Yeah, a few. Good. Yeah, so EJBCA, that's available today that you can use community version of EJBCA to create your hybrid CAs and quantum CAs, quantum safe CAs to issue certificates from the CA, and also you can use sign server for signing using post-quantum certificates, for example, MLDSA, SHDSA, and MS algorithms. And Command, that's our enterprise product. It is also very helpful in terms of migration. So it can do C-bomb, which is a cryptographic bomb, to scan all the cryptography and certificates into the platform, and we can also automate the migration process. Right, so that's a long recap, sorry, and we are talking about interoperability right now. So key factor has been actively participating in the industry hackathons, for example, IETF PQC hackathon, certificate interoperability, SCVP, and testings with different libraries and tools, including OpenSSL, Cryptolib, and WolfSSL, and others, to ensure that the product remain aligned with the current and emerging needs. So our approach is to focus on PKI, certificate and TLS, mutual TLS, encryption and key exchange, digital signing and verifications, and certificate lifecycle management. So for certificate and MLTS, we have tested our certificate issuance using EJBCA with Bouncy Castle at the backend, and issue MLDSA certificates and validate across the libraries, for example, OpenSSL. For session encryption and authentication, we have tested MTLS encrypted with PQC keys exchange and MTLS authentications between OpenSSL and Bouncy Castle. So this test is very important because TLS is the foundation to secure the communications. For CMS, messaging, signing, verification, validation, we have sign server to sign CMS messages and then verify across different libraries, encrypt and decrypt CMS messages across the libraries. Timestamping, we're working on that at the moment. It's still in progress. The test which is critical for co-signing, container signing. We have a lot of discussion today about SBOM signing as well for supply chain security and compliance. And for certificate lifecycle management, we have tested to use our tools at Bouncy Castle EJBCA for CSR generation and issuance from EJBCA for MLDSA keys, SLHDSA, MS, and validate across libraries, OpenSSL and Bouncy Castle. And we also validate our CRLs, OCSPs, and enroll certificates using protocols such as CMP and ACME. Oh, sorry. HSM, which is also the critical part of the PKI, and we have tested against multiple vendors. So that's including Fortanix, Securasys, CryptoFoy, CryptoNext, and Thales CTC. We're working on Thales Luna with Thales team and Utimaco team for PQC testing. So if we put everything together in terms of interoperability, we have EJBCA that integrate with HSM for creating CAs and keys in the HSM and issue certificates, and for signing, code signing certificates, TLS certificates for TLS communications, and we can also leverage client tools like CertBall and other tools for certificate enrollment, and Secure Boot, which is another signing use cases, and different PKI use cases, OCSP signing, and CRL verification. Right, so I've took a quick screenshot from the GitHub, but you can check the GitHub repository and see, what's the testing results from different tools, libraries. Bouncy Castle is the first one. We have been doing very well in terms of different algorithms and testing. So it looks good. We also publish our report, interops report in our documentations. So you can check the link over there. Yeah, to contribute our users, we also come up with PQC Lab, which is a free trial instance where you can test the tools, EJBCA and sign server for certificate issuance and signing using the quantum safe algorithms. So I'm going to do a little bit quick demo. So I'll just change my screen. Make sure it. All right, good. So in my EJBCA environment, so I have created 4 CAs. One is a root CA for hybrid, using hybrid certificates. So we can take a look. The certificates over here, I can see that the signature algorithms is using SHA-2 with RSA as the main signing algorithms, but you can also have alternative signing algorithms using MLDSA 65 algorithm. There's a hybrid root CA, and I use that root CA to sign a sub CA, and also I have a PQC root CA and sub CA, which uses the pure MLDSA for key generation, for public keys and signing algorithms. And I have sign server where I'm going to do some CMS signings in my demo. All right. Just clear my screen, and I'm going to use I'm going to use OpenSSL to generate my MLDSA CSR. So I'm just copy this command, and you can see there's a MLDSA 44, and I'm just generating the CSR and convert the format to B64 encoded format. And then I can use my ESD endpoint to enroll a certificate by using just a simple command, and it's okay, right? So I have a certificate generated from EJBCA. I can also see my certificate content, right? So I can see that certificate was issued from my PQC sub-CA, and I'm using MLDSA 44 key algorithm. And that's a very big signature, right? So it's that's very typical for MLDSA keys. And I can use OpenSSL to do certificate verification. That's okay. I can also do CSR verification, where I download the CSR from my CRL distribution point and just do a verification using OpenSSL. So I'm just using different tools to cross-check and cross-verify. So I can see this CRL is verified okay, and I can see that I have one certificate that was revoked 4 days ago in that CRL list. Right, further down, I'm going to do some signing. So I created a file, and the file is basically OpenSSL SSF Community Day 2025, and I use OpenSSL to sign the messages. I'm using, I can see the signed file in the CMS format, and I can use OpenSSL to verify it. So the CMS verification is successful. Similarly, I can also send to sign server. So I first generate a hash of that file. So I just put the file into a hash using SHA-512, and then I'll just pass that hash to my sign server to do a signing. So that's successful. I can also check the signature. Right? Is the signature in the binary format? We can use another tool, which is available on our GitHub, which is a post-quantum verifier tool, which uses the Bouncy Castle at the backend to do the cryptographic libraries and operations. Yeah, so the verification is successful. It's using my certificates. It's verified. It's all good, right? And I can also test TOS, right? So I can just use OpenSSL, set up a server, and just verify it using client. Oh, there's another dot. Just copy the whole thing. Right, so the peer signature is MLDSA 44, and you can see there's TOS key exchange using the algorithms. All right, that's all I have for today. Welcome any questions.
So I haven't used post-quantum cryptography yet. What are the performance characteristics of like the equivalent of a block cipher? Is it 10 times more?
Yeah, so great question. So I've actually covered that performance topic last year. So in general, we actually did a test against the post-quantum algorithms. In general, that's around 40% to 20% lower than our algorithms that we use today, like RSA and ECC. So we are expecting, in general, the performance drop. If we are fully migrate to those algorithms, MLDSA, for example. But I think NIST is still working on more algorithms and finding more efficient algorithms at the moment. Yeah. That's the answer. Thanks.
Okay, but it's not like orders of magnitude slower, or?
No.
Okay.
Yeah.
Cool.
Yeah.
Thank you.
Thank you very much for this very interesting presentation.
Thank you.
I didn't realize how far the technology had come along. Obviously, post-quantum cryptology is a real important issue. A real fundamental question, though. This shows my lack of knowledge. I've understood that as computers get faster, we need larger keys to simply handle the faster computers. And I'm assuming that a quantum computer is more complicated than just being really fast. So I'm curious as to what we're doing besides just using bigger keys. And I'm just assuming that bigger keys are part of what's happening here. Does my question make sense?
Sorry, can you?
Sure. Okay, I'll slow down a little bit. Okay, so we hear about new computers coming out, and then once upon a time you could use a key that had, say, a couple hundred bits, and now we're told we need a 4K bit key. And I'm just assuming that as computers get faster, we need bigger keys.
Yeah.
And then as a novice here, I'm assuming that a quantum computer is an equivalent of a real fast computer, so the first thing that comes to my mind is let's use big keys.
Yeah,
But
okay.
I'm assuming that it's more complicated than that. So please tell me where I'm wrong and what's happening and what can be done.
Got your question. Yeah, so the keys getting bigger, you have bigger strengths in terms of security, but quantum computer is different. So specifically for quantum computers, it's very efficient to solve the fundamental mathematical problems of the cryptography that we use today, like for example RSA and ECC, especially if you check about the Shor's algorithms. Quantum computer is faster, but it works a little bit different from the computers that we use today, and it's very effective to solve that mathematical problems of RSA and ECC. So that's, they can break the keys in milliseconds. Yeah.
So does that mean that rather than simply making a very complicated factoring problem, we're using totally different mathematical questions that need to be solved that are not... Okay, that makes sense.
So all the quantum-safe algorithms, they are based on different set of mathematical problems. MLDSA, which stands for module lattice based, so it's learning from error, kind of different problems. So it's harder for quantum computers to break.
Okay, all right, thanks.
Yeah.
Appreciate it.
Thank you. Your certificate is based in AS.1. So if you're ready for about standard of X.5 or 9 or some AS.1 standard, if we use PQC-hybrid certificate, we need to standard above.
Yeah, so the standardizations are ongoing, and there are many things that need to be standardized. One is X509, and there's also PQC-11, TLS 1.3. There are many things coming up to be formally and officially standardized. Yeah.
One more question. Yeah. Do you have any plan and strategy scanning and migration traditional to PQC system? Do you have any?
Is the question specifically for scanning?
Yeah, is that
okay.
This time is the hard issue is migration traditional to PQC system. So
yes, okay. Yeah, so PQC migration always start from cryptographic inventory, and which need scanning tools. Like you need to find out all your cryptographics that you use in your organizations. It can be in the even in the source code, in the repository, in your file system. That is very hard to have the full visibility of all the cryptographic that you use today. Thus, you can't estimate the vulnerabilities that you have and exposure in the organizations. So we do have new tools that can do the file-based or more advanced-based scanning, which is coming from our new acquisition from Keyfactor. So I didn't put in the slide here, but happy to share the news and links to you.
Thank you.
Yeah.
Okay, thank you, Tony.
Thank you.
Please big applause.